Those are analyzing the data part. But when we look at generative AI, it is that subset of AI which generates new media, and that media can be images, text, audio, etc. Many people confuse large language models with generative AI, but in fact, text is just one subset or one modality of generative AI. It can refer to image creation, audio creation, and video creation as well. It's just that GPT became famous for text, and that's why many people confuse large language models with generative AI. But even image generation tools like Midjourney, DALL-E, etc., they all come under the category of generative AI. So basically, it's that subset of AI which focuses on generating new stuff, which mimics human creativity. And all of this actually started from 1966. So in 1966, MIT released a chatbot called Eliza, which was supposed to be a psychotherapist, and it answered various questions which you asked Eliza. So let us try to interact with Eliza right now. So I hope you can see this interface. So this is the Eliza interface, which was developed in 1966. So the question here is something troubling you? So let me write that I have been trying to learn artificial intelligence, but I really don't know how to start. That's the question which I'm asking Eliza. So let me click on talk. And then Eliza just says, that's quite interesting. This is not quite useful, right? That's it. That's the end of the conversation. Let me show you one more interesting interface where we can actually talk with Eliza. And I hope you can hear the sound here. So I've chosen the...
How do you do? Please tell me your problem.
So it has asked, how do you do? Please tell me your problem. So I'm going to write, I am unable to learn AI. Please advise.
How long have you been unable to learn AI?
So the question is, how long have you been unable to learn AI? So let me say 6 months.
That is interesting. Please continue.
So that's it. This is not very useful, right? Eliza just told me that that is interesting. Please continue. That's it. It did not offer me references. It did not tell me what I should do. Now compare this with ChatGPT of today. That's the development in 60 years. In 1966, this was the state of the art of generative AI and natural language processing. So this is quite interesting, but it's nowhere compared to where ChatGPT is right now. There is a huge technological advancement which has happened in 60 years. But this also was an example of generative AI because it is generating new output based on how you are interacting with this chatbot Eliza. So it's pretty disappointing now, but in 1966, this was considered to be revolutionary. Then what happened is that after that, neural networks became popular. Neural networks became really popular for prediction tasks and for tasks to predict something such as weather forecasting or let's say classification tasks. But the problem was that generating something new requires us to have information of the past. It requires us to have memory or history. So think about ChatGPT itself. To generate something new, it is not enough to just know one word before it, right? Because we need to know the entire sentence to understand the context. So history and memory really matter a lot when we are trying to generate new output. But the problem with feed forward neural networks was that there was no way to capture memory. There was no way to capture data as a sequence and then use data at the start of the sequence as well as at the latest point. And so simple neural networks were not enough for generative AI tasks such as text generation, etc., because they did not capture memory or history. That's when new developments were made. In fact, starting from 1980, then 1997 and 2017, three significant developments happened in the field of generative AI. In 1980, the first paper on recurrent neural networks was released. In 1997, the first paper on long short-term memory networks was released. And in 2017, the paper on transformers was released. And this paper on transformers now forms the core of the GPT architecture. So important to note that you might have heard of transformers, but nobody really gives credit to recurrent neural networks and long short-term memory networks advancements, which happened in 1980 and 1997. So let us initially look at RNN and long short-term networks so that we can appreciate the discovery which happened in 2017. I'm going to give you a very visual intuition of these two networks so that you will never forget it. So first, let's look at recurrent neural networks. Recurrent neural networks were an augmentation to just feed forward neural networks because they maintain the hidden state. And this hidden state essentially captures information of previous inputs. So you can relate this to the history or memory which I talked about. Since we captured history, recurrent neural networks suddenly opened a gateway for us to generate new sequences of text, music, and that's why they had a large number of applications from around 1980 to let's say 1995 until long short-term memory networks were developed. So let me motivate the concept of recurrent neural networks further. Let's say if you have a stock which is varying like this, as shown in the blue graph, and you want to predict the stock price of this blue company, which is shown in this blue line on day 10. If you want to do this, it is not enough to just have the information of day 9, right? You need the information of all the preceding days to understand the trends, to understand if there are any oscillations which happen frequently. So we essentially need our neural network to be flexible in terms of how much sequential data is being used for the prediction. We need sequential data of the past to be able to make this prediction. Normal neural networks cannot do this, but recurrent neural networks can take input values of the past also to make the next prediction. And the way they do it is because of a significant advancement which they have, and that is this feedback loop. So the way I think about this feedback loop is that if you look at feed forward neural network, they don't have this feedback loop. Everything happens in a linear, straightforward manner. We go from the first neuron or the first layer to the second layer, from the second layer to the third layer. There is no feedback like this. In recurrent neural network, what this feedback does is it allows the interaction between the present and the past. And that interaction is depicted by this arrow over here. And if you want to go back in time, all you need to do is you just need to chain these feedback loops together. So if you chain multiple feedback loops together, you have the provision of capturing a lot of prior data as input. This was the major change in the recurrent neural network architecture as compared to normal neural networks. So the feedback loop makes it possible to use sequential input values like stock market prices collected over time to make predictions. However, again, we ran into a problem. The main problem with recurrent neural network was something called as the vanishing gradient or the exploding gradient problem. The simple way to think about this problem is that when we chained these different feedback loops together, if W2, which is the weight matrix here, has values greater than 1, and if you multiply all of these W's together, if you have 50 or 100 such feedback loops, they will explode. And this is pretty bad because then our loss function will never converge. On the other hand, if W2 is very small, and if you multiply a number of these small values together, these weight values will vanish. So our loss function will not essentially change and we will stagnate while doing the gradient descent. So this was a big problem in recurrent neural networks. And this problem was solved by something called long short-term memory networks, which were introduced in 1997. Now remember that LSTM are a subset of recurrent neural networks, or you can think of it as a slight modification to the RNN to address the vanishing gradient problem. And the way LSTM work is something like this. Long short-term networks or long short-term memory uses two separate paths to make prediction about tomorrow. If you look at a recurrent neural network, each feedback loop just takes the present value and the value before it, right? It does not take the value from long time back. Long short-term memory uses two separate paths to make prediction about tomorrow. The first path which is uses is for long-term memories. So something which has happened way back in the past. It takes into account these long-term memories, and along with these long-term memories, it also takes into account short-term memories. So basically the prediction which it makes is based on the interaction between the short-term memories and the long-term memories. Intuitively, what this does is that it helps us to capture a lot of information about the past, and that helps generating the next sequence of data much easier. So this is the advantage of LSTM over recurrent neural networks. So I won't go into the LSTM architecture in detail, but I just want to show you two things. So this is how the architecture looks like. If you look at the top, there is a green line running through the top, and there is a pink line running through the bottom. This green line is the long-term memory, and it essentially carries information of way back in the past. And this pink line over here is the short-term memory, and it carries information of just something which has just happened in the recent past. And this green line and pink line essentially interact to give us the generated output of the next particular state or the future prediction. So now if you want to predict the stock value of what will happen on day 5, what the LSTM does is that it takes into account day 1, day 2, day 3. So day 1 will be the long-term memory when we are predicting for day 5. And day 4 will be the short-term memory when we are predicting for day 5. And both these will interact to give us the final output. So this is how long short-term memory networks actually work, and these were invented in 97. So let me give you a demonstration of RNN, and then I'll give you a demonstration of LSTM. So don't worry about these links. We have made a document where we have collected all the resources which are presented in this webinar. So we'll be sharing all these links with you. So the first demonstration is an RNN, and I want to demonstrate it through a simple summation. So let's say I write 1 plus 20. Now you might be thinking that how is this an example of RNN? It turns out that we can actually train a recurrent neural network to calculate this. And the way to do that is not look at these as numbers, but look at it as a sequence of characters. So the first character is 1, the second character is plus, the third character is 2, and the fourth character is 0. And we are asking the neural network to predict the next characters based on these earlier characters. So this, if you understand this, this is at the heart of even how ChatGPT works. We take tokens or we break down the sequence into characters and we predict the next character. So now if I calculate, if I click on calculate, you can see the prediction. It has predicted character 1, the probability. So this is a probability distribution, and the maximum probability of the first resulting character is 2. The maximum probability of the second resulting character is 1. So it's 21. And for the character 3, it says that the maximum probability is the space bar, which means we end it over here. So the answer is 21. One thing you should remember here is that the output is given in the format of probability distribution. And then we select that character which has the highest probability. So this is an example of recurrent neural networks. With LSTM or with long short-term networks, we can do things which are a bit more advanced. We can create recipes. So if I type pizza here, text length of 800, and there is something called fuzziness parameter of 0.6. And if I click on generate, now this is a bit more complicated task than this thing, right? Than this number summation. But you can see that LSTMs are able to do this. They are able to generate the recipe of a pizza. In fact, you can type anything here and it will generate the recipe of that. So you can already see that it's kind of, it's a small tiny version of what ChatGPT is capable of right now, but it is still quite amazing that it is able to generate recipes. So RNN and long short-term memory networks are an example of generative AI, but they are just not as good as ChatGPT. I'll also be sharing the Google Colab file for this RNN so that you can take a look at it. Now, we saw that RNN and LSTM could do some things, but they definitely cannot summarize paragraphs the way ChatGPT does right now. They cannot pass the legal examination tests. They cannot solve problems of competitive examinations like how ChatGPT does. So one major advancement happened in 2017, and that was the introduction of transformer architecture. So transformers actually do not rely on recurring portions of sequences like RNNs and LSTMs, but rather they use something called as the self-attention mechanism. And I will explain what self-attention mechanism, or we have that covered in the latter part, what self-attention mechanism exactly does. But right now, all you need to know is that transformers can process the input sequence in parallel, whereas LSTMs and RNNs process the sequence one element at a time. What a transformer can do is that it can process entire sentences in parallel because of the self-attention mechanism. And this kind of a parallel processing enables transformers to be much more efficient and faster when dealing with long sequences. And this is at the heart of ChatGPT. In fact, after 2017, in 2018 itself, GPT architecture was released by OpenAI. So remember that GPT architecture is just a version of the transformer architecture. And this was the main thing which really put LLMs in the spotlight. And this turned out to be the model which could do a huge range of practical tasks. But to appreciate GPT, I want you to just appreciate this historical journey. Remember where we started with? We started with ELIZA, which was pretty bad, as I showed you. Then we went to recurrent neural networks, 1980. Then we went to long short-term networks in 97. Then transformers came in 2017, and then finally GPT came in 2018. And GPT is the reason we are having this webinar right now, because there's so much hype and so many job opportunities in the generative AI space because of this. And after GPT, today the state of the art is that we have large language model with billions of parameters. As you can see, here is GPT-4. Then we also have Bard, which is Google's. Then Claude. We also have Llama, which is Facebook's. These are large language models with more than a billion parameters. And this is the state of the art in 2024. So this was the history of generative AI, so that you can appreciate what we are going to learn in the subsequent modules. Now, after I learned about this history, I wanted to start learning about large language models because they are the ones which form the core of GPT. But I did not know where to start. I wanted to understand the basics of how GPT works. So then I came across a very nice GitHub repository by a very famous machine learning practitioner called Andre Karpathy. Many of you might be knowing about him. And this is an amazing repository to get started with building your first large language model. Let me explain what the Makemore project is all about. In the Makemore project, you have a set of baby names. So the names can be Emma, Olivia, Eva, Isabel, etc. You have a list of 35,000 baby names. That's the data set. And what we will do using this Makemore LLM is that we will feed it a database of the names, and Makemore will generate cool baby name ideas that sound like names but are not already existing names. So basically, based on this data set, we'll come up with new names, completely new names, which will sound as names, but they are not based on data set. And we will train a large language model to do this. This is an example which can be run locally on Jupyter Notebook, and I'm going to show those notebooks and share them with you. And I want you to appreciate how simple it is to run this. So let us start understanding how to generate these new names and how to construct your first LLM. So I have this kind of a drawing board interface over here. And one thing to remember is that the Makemore project is a character level LLM. So basically what it does is that you train the LLM based on characters. So you have the prior character, then you guess the next character based on that. After you guess the next character, you guess the character after the second character. So let's say these are the names which are in our data set. The question is, can we look at these names and generate more names like these? So let us figure out how to do that. Forget about LLMs. Let's say if you had no idea of LLM, how will you go about solving this problem? Let's say I construct some boxes for the first character, the second character, third character, fourth character, etc. of the new name. So how will I choose what the first character is? Intuitively, what we will do is that we will choose the character which has the highest probability of being the first letter. And how will we do this? Based on our data set. We'll look at our data set and see which character appears the most. And then we will choose a character which has the highest probability of being the first letter or the first character. So after the first character is chosen, then we will move to the second character. And how will we determine what the second character is? Let's say the first character is finalized to be A. Again, we will look at the data set. We will look at all the names starting with A, and we will look at which is that character which comes the most after A. Then we will fix this to be the second character. Then similarly, based on the second character, we will fix the third character. So that's why it's called as a character level LLM, because the next character prediction only depends on the previous character. So this is the basic naive way in which you will generate a new name without even knowing anything about large language models. And that is exactly the first approach which we are going to see. So there are two approaches which we are going to see, which will generate new names. The first approach is just based on probabilities, and the second approach is based on a neural network training. So I'm deliberately explaining everything in this kind of a drawing board interface, because then the code will be much easier to understand. So in this approach, let me show you what we are going to do. We are going to look at bigrams. So someone in the chat has already mentioned about n-grams. We are going to be looking at bigram. And the simplest explanation of bigrams is that it's a sequence of two characters. So what I will do is that so what are the possible bigrams? AA, AB, AC up to AZ, BA, BB dot 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 up to BZ, and ZA, ZB dot 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 up to ZC. Okay. Then what I will do is I will look at my data set and count how many times these bigrams are appearing. Let's say this is 4 times. Let's say this is 5 times. Let's say this is 6 times, etc. And I will create a matrix of this count values. In fact, this is how that matrix will look like. So this is that matrix of the count values, and it's pretty simple to understand what this matrix represents. We have 33,000 baby names, and let's look at the row for A. So AA comes how many times? That's 1,112 times. AB comes how many times? This particular cell shows AY comes how many times. So wherever you go to, it represents how many times that particular bigram appears in our data set. So if you look at this, so IO comes 1,176 times. So that is the initial thing which we are doing with respect to this data set. We collect these bigrams and then we count how many times they are appearing. Then what we do is something very simple. Look at the first row over here. The first row represents the number of times that particular letter appears at the start of a word. So this particular 8,820 is the number of baby names starting with A. 2,612 is the number of baby names starting with C. So if I ask you the question, based on this first row, what character will you choose for the new name? What the new name is most likely to start with which character? And you will look at the first row and you will look at that particular cell which has the highest color or the highest number. So that is A. So A is most likely to come. So in fact, what we will do is that we'll convert this entire row into a set of probability, into a probability distribution, and then we will sample from that distribution. When we sample from such a distribution, since A comes most of the time, most likely we will sample A. We will also sample B, C, etc. So this is what we are going to do. So let me again show here. So the first question we ask is what is most likely to be the first character. Then we construct a probability distribution based on the first row, which we saw over here. And then we sample from that probability distribution. That's how we are going to choose our first character. Then after we have chosen the second character, let me tell you what we are going to do. So let's say the first character is C. Let's say we sample C from our probability distribution. Then we are going to this third row. And then we are going to look at which is the most common letter which comes after C. And I'm going to choose the letter which has the highest value. So here CA has 1630, which is the highest value. So then A is most likely to come after C. So that's how I'm going to choose my second character. Similarly, I will choose my third character and I will stop when a dot is returned. So dot means that we are at the end of our sequence. So this is how I'm going to generate new names based on the probability, based on the method of probabilities. So when I share this code with you, you will see that this is exactly what is done. We sample from the probability distribution and we generate names. So here you can see I've run this same thing what I've written in text right now. I've run it 10 different times. I've run it 10 times and 10 baby names have been generated. As you can see, of course, they are not quite good because we are not using even a neural network. We are just using a probability distribution. But these are the baby names which our simple probability distribution model has generated. Now I want to show you a second framework, which is a neural network training. And the way this is done is exactly how ChatGPT operates at its very essential or at its very base form. So let's say I look at this word Emma. If you look at this name closely, it actually has 5 pairs of input and output. So the first pair of input and output. So first is just we are starting with nothing. So this is the input one and the output is E, which means we are starting with E. Then the input is E and we are predicting what the next letter would be. So the next letter is M. Then the input is M and we are predicting what the next letter would be. That is again M. Then the input is M and the next letter is A. And then finally the input is A and the output is a dot, which means we end there. So here there are 5 pairs of input and output. And now what we are going to do is that for every single word in our data set, we are going to train a neural network which takes this first column entirely as input and this is the output. And we are going to train the neural network on the entire data set with input output pairs generated exactly like what I showed you right now. There are some tricks done to train this neural network, such as when you look at a particular letter such as E, one hot encoding is done. So for example, there are 27 characters, right? And E, A, B, C, D, E. So it comes, so including the dot, then A, B, C, D, E. So E will be represented like this. It will be a vector of zeros and only the sixth will be 1. Similarly, all alphabets will be represented by this one hot encoding. And what I will do is that, let's say this is my input E, and this is my neural network with 27 neurons. And I will train this neural network. And the output of this neural network will be 27 outputs. And then I will look at what is the output which is most probable. Of course, when the weights are not optimized, these outputs might give the wrong value initially. But when the weights are optimized, we hope that when E is put as an input here, it will give M as an output. When M is put as an input, it will give M as an output, etc. So then we will train the neural network through gradient descent. That is the main idea behind this second approach of neural network training. And this is exactly what is done in the code. So the second part of the code is building a neural network. And this is the same thing which I showed you right now. Input output pairs for the word Emma, then one hot encoding. And then one thing which I want to show here is that, okay, so let's say this is let's look at this highlighted part. Okay, this means that the input is E and M, which is fed to the neural network, and we know that the output should be M. So the actual next character is M, whose value is 13. But look at the probabilities of our neural network. This is when the weights are not optimized, and these are probabilities for every single character. And let's try to find which character seems to have the highest probability. And it looks like probably, so 13 is definitely, so 0, 1, 2, 3, 4. So this is 13 and it's very low, which means clearly this is not trained. So when the neural network is trained, we expect the probabilities to be arranged so that the 13th character has the highest probability. And then finally we do gradient descent. What I have shown over here, this is the gradient descent optimizer. And then we employee gradient descent, and then we again predict what the baby names would be as an output. Again, this is not a great output because we are not even using a recurrent neural network here. We are using a simple feed forward neural network. So this is the Makemore project part 1, and I'm going to be sharing this Jupyter notebook with you. So when I share it and when you look at this code, everything is exactly similar as what has been written on the whiteboard over here. So you will understand it completely. In fact, I'll share another notebook with you, which is Makemore part 2. So someone mentioned n-gram on the chat, right? So this is a bigram. So basically we are just looking at the earlier letter. We are just looking at one character to predict the next, right? But what if we look at multiple characters? So let's say these are, what if we look at 3 previous characters to predict the next one? This can be done, and I have showed how to do it in the second Jupyter notebook. This is also the notebook provided by Andre Karpathy. So we have to just look at the block size. So how many characters do we take to predict the next character? And you can set it to anything. This is the beginning of understanding context, which is so important to understand how ChatGPT actually works. The simplest way to understand context is how many characters do we need to predict the next character. So in this section, I'll be sharing the following things with you. This RNN interactive demo, LSTM interactive demo, and the Makemore part 1 Jupyter notebook, and the Makemore part 2 Jupyter notebook. So up till this point, we have intuitively understood how to use previous characters to predict the next character and generate probability distributions. So this is the main idea behind the simplest project to understand large language model is to first understand the Makemore project. So we looked at Makemore part 1 and we looked at Makemore part 2. Now it is time to start understanding transformers and to actually start understanding the attention mechanisms which makes GPT so powerful. So Shridat will be covering this section. So I'll just stop sharing screen now.
All right. Thanks, Raj. Hope I'm audible. Can you see the screen?
Yes, yes.
Okay. So attention is all you need. This is the paper that revolutionized everything. This paper was published in Archive in 2017 by a team at Google, and currently this paper has been cited more than 1.2 lakh times. And this anyone in scientific community knows that this is a very, very huge number. And this is the paper that for the first time proposed the transformer architecture as we see in its current form. And to fully understand the working of transformer, it is very, very difficult, and it will take you definitely more than multiple hours. So I will not wish that I can make you understand transformers in today's webinar in the 1/3 of the time that I have, but rather I will briefly touch upon how a text is represented, how it is converted into a format that these models can understand, and how exactly does attention head look like in its simplest form. So I will walk you through that much, and then after that, instead of going into more theory and working of transformers, we will go through how we can implement a GPT ourselves hands-on. If you are interested in understanding more about transformers, there is this nice video by 3 Blue 1 Brown. This is a great channel. I highly recommend everyone to subscribe to this. Just have a look at this video. They have 2 videos in this series. One is about attention in transformers, and the previous video on this was on ChatGPT. We'll also, ChatGPT meaning how ChatGPT works and how the transformer architecture makes it happen. So we will be sharing the link for that too in the Google Doc. And this is the attention is all you need paper. We will be sharing the link to that this also, but I'll just share the link to this paper in the chat just for your quick look. So this is the transformer architecture, and don't worry if this looks very intimidating. It does look intimidating even after you have a look at it multiple times. So So in a very simple term, transformer is a type of neural network architecture. There were several other architectures which was before BERT and several others for natural language processing tasks. But till date, transformer is the best one that we have been able to come up with. So let's imagine that we have a language related task which is converting an English sentence into its French translation. I don't know how exactly to pronounce it. It's ceci et un chat. So it's like this is a cat. So Raj showed how recurrent neural networks were really good at these tasks, and indeed recurrent neural network is quite good for performing tasks like this, where these words are not, you cannot look at the 4 words in this sentence independently, because these words have a meaning only in a particular sequence. So if the sentence was something like all cats are animals, and let's say you swap cats and animals, so all animals are cats, so they are completely different in terms of meaning. So you need to consider the sequence, and for that reason recurrent neural networks were actually quite good for that. But the problem with RNNs is one of the main reasons why transformers and ChatGPT ultimately became so successful and popular is because you can parallelize your computation so much. So you can divide the entire sentence into n number of tokens, and you can use those tokens parallelly all at the same time, which is difficult to do in recurrent neural networks. So that's why transformer architecture became very popular. And transformer architecture can capture, so this is a sentence with the length of the context is very small, but you must have used ChatGPT, and you can even copy paste very big paragraphs, and the transformer architecture essentially can capture long-term dependencies. So by long-term dependencies, what we mean is you will not lose the context going from the first word or the first token to the last one. But if you remember, when GPT 3 was there, if you continuously did chatting with GPT 3, by the time your chat reached very much down, GPT will completely forget what was the original topic of conversation about. It will go into a tangent. But this issue is solved to a great extent in GPT 4, mainly because it has much higher, the context size is much higher. So a transformer architecture has 2 units, encoder unit and decoder unit. Let's look at this in brief. So let's say the task that we have is convert this is a cat from English to French, right? So the English version of this is the input. The French version of this sentence, which we saw earlier, is the output. So first step in this whole process is called tokenization. This is a very simplistic representation of tokenization. In reality, this is not how tokenization works, but I don't want to go into the complex details of what exactly the tokens look like. But for simple purposes, let's imagine tokenization means dividing a sentence into its constituent words. So this is a cat is divided into 4 words. So that is the step 1. The second step is something called as embedding of these tokens. So what is embedding? We have a section dedicated to this in the later part of the presentation, but I'll touch upon this very briefly right now. So embedding meaning a computer cannot process English words, rather you want words to be represented in terms of numbers. And Raj showed you how one-hot encoding can be one way to represent these words, right? So 0001000. So let's say you have a dictionary of words. If you are referring to the first word in the dictionary, it could be 1, the representation could be 1 followed by a bunch of zeros. But in reality, one-hot encoding is not ideal for this. We'll show why this is the case. So in reality, this embedding is done using a set of real numbers, and the length of this will depend on what kind of transformer architecture we have. So this is how it looks like when you convert tokens to its embedded form. And all of these tokens in its embedded form is fed into the transformer network all at once. So this is what makes this transformer architecture much more powerful compared to recurrent neural networks. So, but here is the problem, right? The problem is, let's say I chop the sentence into 4 different words and feed it into the transformer network. how does the transformer network know that this word comes first? Because that order is very important, right? All cats are animals, or all animals are cats. Those are two different sentences. So yes, it is fine to chop the sentence into tokens or words. It is fine to convert those tokens into embeddings. But where is this positional information included if we are feeding all of these tokens at the same time to the transformer? So the place where this position information is encoded is within the value of the of these embedding itself. So the initial embedding that is created is slightly changed using a particular function, and it's a bit complex function what the attention is all you need paper uses, but basically these values change slightly such that the positional information about this word is also embedded within the data of the word. So so this is called positional embedding. To give you an example, let's say I am, this is a very simplistic way, okay? So let's say the data about this word is this, these letters, THIS. Imagine I'm also adding a letter 1 with, a number 1 with this to denote the position 1 of this. And let's say this is added with a number 2, this is added with a number 3, and this is added with a number 4. So now, along with the original data, which are these words, you also add a positional data in its most simplest terms. So that's exactly how positional embedding works, but you are not adding 1, 2, 3, 4. It's a bit more complex than that. So unlike RNN, so here what we do is, even if the length of this sentence increases, you can easily embed the positional information by changing the underlying data. But in recurrent neural networks, you had to make the neural network itself much more complex to deal with a large set of words to take care of the positional information. So now what we do is, so this part is a little bit tricky. So let's first look at the encoder part of the transformer architecture. So let me go back a few slides. So if you remember the transformer architecture, this is the transformer architecture. So currently we are focusing on this left part, which is the encoder. This right part over here is the decoder. Okay, so let's look at the encoder first. So this encoder has something called self-attention layer, and this is the, you can call this as the backbone of the transformer architecture. So what we do here is, once we tokenize and we convert the token into positional embedding, these embeddings of these individual tokens have 3 sets of values called query, key, and value. So what are we trying to do here? We're basically trying to establish how these words are interdependent, right? So a word like cat will be in a different context if it's in a different sentence. Or let's take another example. Like a word like quill. Quill can have 2 meanings. It's in one sentence it can mean the writing tool. In another sentence it can mean the quills of these porcupines, right? So same words can have different meanings and different association with other words. So query is like, imagine that the word called this or this token is trying to actively look for other words within this sentence, like other words meaning is, a, cat, etc. So query is like it's an index of how this word is trying to look for other words within the whole context. Don't worry if you cannot visualize this properly, or if you cannot fully grasp what exactly does this mean. It takes probably more than a few hours, and you need to consume a bit more details about the transformer, but I am just trying to give you a qualitative overview. So query is like, it's an index of how this word is looking towards the rest of the words. Key is an index of how the rest of the words are looking at this particular word, right? And value is the information or the inherent meaning of the word. So inherent meaning the words, if you just take the word in isolation, it will have a vector embedding, right? Not the positional embedding, the one before that. It will have a vector embedding like this. So basically that. So that is query, key, and value. Then what we do is, we will find query of this with all the other words, with the keys of all other words, meaning how the word called this is seeking out other words, and how these words is, a, cat, how those words are being seeked using the keys. So query means how the word is seeking other words. Key means how that word is being seeked, right? So so query of this with key of the rest of the words, query of is with the keys of rest of the words, query of a with the rest of the words, and query of cat with the rest of the words keys. So essentially in the self-attention layer, what happens is it creates a matrix that kind of looks like this in the simplest format. So these are the queries of the words, and these are the keys of the words, and then it creates like a mapping, meaning it creates like a similarity score between the query of every single word with the key of the same words. And here several things are done to make sure that, I mean, we don't get any extra information to know that this word called this is highly correlated with the word called this, because that information we already know. So steps are taken to ensure that the correlation score is not maximum along the diagonal, and several other more steps are done to make sure that these set of values look like a probabilistic distribution. So Raj showed how softmax can be used to create the probabilistic distribution. So a softmax function is applied to this each of these, such that you have a probabilistic distribution of these query to key mapping. And basically this is how one layer of attention looks like. So essentially you can understand the degree of correlation between two words. So if you have let's say professor and Harry and let's say Snape, these words in a sentence, some of these words are very highly correlated. Maybe professor and Snape are very highly correlated. So if one of the query here is professor and the key here is Snape, the corresponding value to that, which is the size of this red circle, will be proportionally higher. So this is one example of the self-attention layer. I highly encourage all of you to go through the 3 Blue 1 Brown video. Each of the videos are around half an hour. It takes some time maybe you will have to watch it 3 to 4 times, but please do that to understand this in a much better way, right? So once the self-attention layer is formed, and there are actually 96 different attention layers in GPT-3, for example. In some cases it's much more than that, in some cases it's much less than that, but basically then several other operations are done to normalize, and there is a multi-layer perceptron, and ultimately the output of this embedding, this encoding is sent into as the input to the decoding part. So and here the output of the final French sentence, which is this, is also provided, and ultimately this is how the training of the transformer architecture happen. Basically decoder is responsible for generating the input, encoder is responsible for creating the relation between various tokens within the input. All right, I don't want to go into too much details of decoder because that's not the purpose of today's talk. Today's talk is more about how you can run a simple GPT yourself, so that you yourself can build an intuition of that. So Raj mentioned about Andrej Karpathy. So last year he released this legendary video. This was about building a GPT completely from scratch. So it's a 2-hour video. It will take you it will take you definitely much more than 2 hours to go through this. But if you are very interested to understand how GPT works from scratch, and this basically will make you understand every single thing that is mentioned in the attention is all you need paper, or even in the 3 Blue 1 Brown video. So the best point to start is probably 3 Blue 1 Brown video, and then if you have time and if you have interest, I highly recommend you to go through the Andrej Karpathy video. But basically in this video he has built something called nanoGPT. So this is the nanoGPT GitHub repo. So what we will do today is, let's try to run the nanoGPT on our own computer. So this is a very simple architecture, so we can even run it on our own computer. So I have tried this already, and I can run it on my own computer, even though I have GPU. Since I'm not having NVIDIA GPUs, I have AMD and Intel. I cannot use it right now. So I'll be running it on my CPU instead of GPU, and I'll show you how we can train a large language model, a small large language model, to learn from some of the works from Shakespeare, and how it can create some output that resembles Shakespeare's work. So So here basically what nanoGPT does is, here is an example. So if you are able to run on GPU, you can output paragraphs that look like Shakespeare's work. I'll get to this in a moment. So to start, let us first start with forking this repo. I'll fork this. Let me go back. So you must have seen these stars, and this is a very highly 32K stars is very difficult to achieve for any GitHub repo, and many people have tried to fork this. So let me fork this. Okay. So I copy this into my GitHub repository, and okay, now that forking is done, let me copy this and let me clone this in my remote. Okay, so I have cloned this, and so I'm using GitHub desktop. I'm not using terminal. I find this very convenient. I encourage you to try this, and then I can open the code in Visual Studio Code. All right, fine. So now there are 3 steps that they mention. First step is to create the data set. So create the data set meaning create training data for training the LLM, create validation data out of the work from Shakespeare. So I'll show you how the input data look like. So so let me go to the data over here, the Shakespeare car. So this is the data set preparation Python code. So initially, let me do one thing. Let me create a virtual environment for myself. So I'll be running all of my code in this virtual environment so that I can show you everything from scratch, from adding the required packages and everything from scratch. So in this virtual environment, I don't have any packages installed. So I'm creating this virtual environment called my virtual environment. So so once this is created, you will see this my virtual and here in the bracket. Yeah, as you can see here. Okay, so now in this, if I try to run this, I'll for sure see that NumPy is not defined. These things are not defined because these packages I have to add. So what I'll do is I'll copy paste this, which I have written for installing packages. So let me install all these required packages. NumPy and all are very famous packages. I'm sure most of you know about this. And while this is installing, let's look at the 3 steps involved in the process of training and creating this output using a GPT. So there are 3 steps. The first step is training itself, preparing the data. And preparing the data meaning we'll be fetching the data in the form of a input.txt file. This txt file has all the works of Shakespeare compiled into one single document. And then using this, we will create training data and validation data. And then after that, so once the data preparation is done, the second step is training. And then the third step is testing or creating the output, right? So these are the 3 steps. So currently we are still in the first step. We are in the step of creating preparing the data set. These packages are getting installed. It won't take more than a minute. So let's wait until that is finished. But what I'll do meanwhile is I will so what we have to do next is to run this file called prepare.py. This is the one which prepares the data set, which is here in this link. So I just opened this link so this document which you see, this is very big. You can see the scroll bar here. This is very big. This is the entire compilation of Shakespeare's work. And you just look at the format. I hope the font is visible. I'll just make it a little bit big. Look at the format, like there are dialogues between different characters and there are paragraphs. So it has a very specific format, and we'll see how when the output is created, how the output looks like. Okay, so let me first run this to prepare the data set. So here you should focus on this folder called Shakespeare car, because here is where the training data and the validation data will be created. So yeah, so you can see that first the input.txt, which is the Shakespeare's work, is fetched here, and then based on that training data and validation data is created. And here you can see some details. So these are all the 65 different unique characters used in this entire document. So it has all of the English alphabets, and it has some special characters and 1 or 2 numbers. So these 65 characters form a vocabulary of 65, and this is what is used for creating the entire Shakespeare's work. Now, one thing you should note is when we are now predicting, so here the number 5 is not there, or number 1 is not there. So since that is not part of the training, of course, it also won't be part of the output. So when the GPT is predicting an output, it cannot have characters which are outside of this vocabulary. Okay, so now the part 1 out of 3 is done, which is preparing the data is done. Now let's do the training. So for training, this is the step that if you have a GPU, this is the step that you should do. Basically, you run this part of the code. You run this part of the code. It has several different parameters defined for people who have GPU. I won't be using this. If any of you have GPU, once you get the code, please try to run this. Instead, what I will do is I will run the training, but at a a configuration that is a bit notched down. So I will copy this part of the code. This dollar symbol, this dollar sign is not needed for me. That's why I did not click copy. And I will be training for 2000 iterations. So here you can see that the device is CPU. It's not CUDA. It's not the NVIDIA GPU. And here I am running this train Shakespeare character.py, this file. Okay. So let me click. Hopefully this should work. Okay. Let me check what has happened. Yeah. Because I came out of the virtual environment, so this was the virtual environment. So let's hope that this runs. So once it runs, you will see the iterations progressing from 1 all the way up to 2000, and you will also see that the loss is decreasing. So here you can see that the loss is starting with 4.1, 4.2, and it's decreasing continuously. So already we are at 100 iterations. So this is running quite fast. So we can maybe wait till 1000 iterations or something, which won't be ideal, but that's okay. Okay, in fact, this has never run this fast when I tried it myself. For some reason, now it's running very fast. Whatever, so we can probably wait a little bit. It won't take more than a couple of minutes. But one thing you should note is this loss decreasing continuously, right? And once the training is finished, I will interrupt the training at around 1000 iterations. I don't want to spend too much time since you get the point. And once the training is finished, what we'll do is we'll run this piece of code, which is creating the output. So let me copy this already, and yeah, I think this is good enough. Okay, I just interrupted this. 1000 iterations, this is good enough. And now when I input this, now this is the phase where our trained GPT, so the GPT with some very minimum parameters, which was trained on this input.txt file. So this txt file had all entire work compilation from say Shakespeare. Now this output is based on our 2 minutes or 1 minute of training. Let's look at the output first. You can see that the format is very similar. So there is some character name, there is some dialogue between 2 characters, but you can see that some words do not make any sense. Like I don't think these are Shakespeare's words. I think these are nonsensical words created by our GPT. Some words are legit. It kind of looks like English, but you can see that there is so much misspelling and everything. But this is what we can expect from a GPT that is just trained for 1 minute. But still, this is good. Maybe if I had ran the iterations for 2000, maybe it would have given me a good output, right? But basically, what we did right now is we trained a GPT from scratch, a very lightweight GPT from scratch, and on a particular data set, and now it's able to produce an output based on that data. Now let's do one more thing. Let's try to train it on a different data set, like let's say a set of songs, using the lyrics of songs, and let's ask the GPT to create a song based on a cue that we provide. So what I'll do here is million song dataset Spotify. So Google Kaggle million song dataset by Spotify, and you will find this particular dataset. Hopefully the Kaggle screen is visible for all of you. So there is this dataset. It's a CSV file. The structure of the CSV file is like this: artist, song name, link to the song, and the text. So text is basically the lyrics of the song. So we won't be using any of these three columns. We will be only using the last column. And this is a huge data set. The entire CSV itself is around 75 MB. I have already downloaded this, but basically we download this and we use this CSV file for training the GPT once again. So what I'll do is, like, here in the data set, let me create a folder called Spotify. And here let me create a prepare.py notebook. And what I will do is I will copy paste first this entire code here, because code is mostly the same except for which data we are using. The next step is I have the data set somewhere here. Yeah, so I have the Spotify data over here. I will first paste this into here. Okay, I just pasted the Spotify dataset CSV file, and now what we do is, since we are not using the data provided by Andre Karpathy of the Shakespeare's work, let me delete the lines that correspond to that. We don't need any of this. Since we are using a CSV file here, we need pandas as PD. So we import pandas. So we'll be using pandas data frame. So let me first copy the piece of code for reading the file. So first we read the CSV file. So let's provide the file path here. File path is data / Spotify / okay, so this is the file path. And next what we do is, so we loaded we read the CSV, and then we want only the column corresponding to text. If you remember from the Spotify dataset, only this text column is having the lyrics. So we train using the lyrics to create lyrics, right? So let's open that. So we read the column, and then what we do is we concatenate this column into one single string, and the string is basically separated by /n, the new line character. So each song lyric will be separated by a new line character. So I will rename this as data, because data is the variable name that I am using. Okay, I think this much is good. So we can now prepare the dataset. So currently, if you look at this folder, we don't have the training dataset and validation dataset that we are going to prepare right now from the Spotify dataset. So let me try running this. I hope this works. Oh, I guess I'm not in my environment. Let me go back. Okay, so these are all the unique characters within the dataset. So in Shakespeare's, you saw all the unique characters. Here, these are all the unique characters, and now the training and validation data has been created. All right. So now we have to do so dataset preparation is done. Step 1 out of 3 is done. Now it's a step 2, which is creating the training dataset. So what I will do is I'll copy this train Shakespeare character, and I'll create a train Spotify. Okay, and here I paste this, and I want to create an output directory called out Spotify, and my project name is Spotify because that's where my folder is. Dataset is also Spotify. So I just changed this, and now what we can do is we can run the code for training. So the code for training which we use, since I don't have a GPU, the CPU, the code where I can run using CPU was this, right? So I have copy pasted this code here, except instead of running the train Shakespeare, I'm running train Spotify. I hope you can see this. So I copy this and paste it here. So I'm running the train Spotify.py, that notebook. And again, this is for maximum 2000 iterations. Hopefully this will run. Okay, so this is also running again. We will pause this at 500 or so iterations. I don't want to wait. And the output that we are expecting is, hopefully we should be able to create some song lyrics based on some input that we give, a cue that we give. Let's see, it may be good, it may not be good. Usually with 1 minute or 2 minutes of training, the GPT that output that we get is not very good, but let's see what we can get. I think I'll pause at 500 iterations in the interest of time. Okay, and now I will, this is the third and last step, which is producing output. And here I can actually give a starting cue. Let's say starting is something like maybe love. So let's see what kind of output we can expect. Okay, so here is the poem, the lyrics of the song that GPT created. It's probably the worst song that you would have ever seen, but in 2 minutes we trained the GPT to produce something what a 3-year-old kid might write. It starts with love. I don't know why it's followed by gore, but it's interesting. There is a lot of spelling mistake, but it's something. So this is in a nutshell how you can run GPT. We have created a full video of how exactly to do this. We will share that with you. There is a YouTube video link. It's part of the Google document. So just go through that in case you have missed something today. Of course, we'll be sharing the recording, but the video will be a bit more better. So this is exactly how you can run, train your own GPT and run it and make it do things for you. So now the one concept that we discussed during the first part of transformer architecture was vector embedding of words, right? So words in English, you cannot use English words in transformers or in general in computers. You need to represent it using numbers. So we discussed this, like what if we represent it using something like, let's say dog is the word and we have a dictionary of all words that are ever existing. And then we create a one-hot encoding like this. How about this? What is wrong with this? The problem with this is, let's say we have a word called dog and puppy. Since in a dictionary, the dog and puppy, like if it's an alphabetical dictionary, D and P are far away from each other. But the meaning of dog and puppy are kind of the same, right? But if you look at the one-hot encoding of dog and one-hot encoding of puppy, they might look completely different, because the one here, one in the dog will be somewhere in the beginning and one in the puppy will be somewhere towards the end of the sequence. So what this means is one-hot encoding cannot really capture the actual meaning of these words, although it can represent these words as in form of discrete numbers. So what a better way of representation would be, ideally, creating a n-dimensional space. So in this particular picture, we are showing a 2-dimensional space. In this space, the words of similar meaning should lie in the vicinity of each other. So here, pretty, attractive, lovely, these words lie close to each other. These words all lie close to each other. Same with this. So an embedding like this is ideally what we need. And look at this example. This is from 3 Blue 1 Brown video only. So here, if you subtract from, so E of means embedding. So if you look at the embedding of queen, and if you subtract embedding of king from that, so it's basically from the feminine, you're subtracting the male version. The difference between these vector embeddings, the resultant vector is approximately same as the resultant vector of embedding of woman minus embedding of man. So what that means is this vector, the resultant vector, which is the subtraction between the embedding of queen and embedding of king, denotes the direction of kind of like a direction of something like the gender. A similar example is embedding of niece minus embedding of nephew. It's the same thing, right? Embedding of woman minus embedding of man. So let's do a simple, quick coding tutorial. It's very interesting actually. So I have already, oh my god, I think since my runtime has been disconnected, let me see. I hope this works. If it doesn't work, I'll have to come back to it, but no problem. Okay, all right. So this is working. So what we have here is we have an already trained word to vector embedding on Google News, and we are using this already embedded data. So currently here we are printing the word computer represented in the vector embedding format. So this the dimension of this is I think 300. So it's like an array. Now let's look at an interesting example. Firstly, let's try to print. Let me delete this so that actually let me delete all the outputs. Let's look at this one, right? So here what we are doing is we are adding the vector embedding of king with vector embedding of woman, and we are subtracting man, the vector embedding of man from this. Can you predict what might be, not like what might be, what all could be the output of this? You can just write in the chat what might be the output of the vector embedding of resultant of the king vector plus woman vector minus man vector. You can put it in the chat. Just try to randomly guess. So king is the ruler version of male ruler. So you are adding a female dimension to it by adding the vector of woman, and then you are subtracting man from that. So basically at the end of it you will get another vector, because you are subtracting, like you're adding vectors to create, adding plus subtracting a vector to create a new vector. So actually it will be queen. Someone has responded queen. Yeah, that is correct. So if you look at the top word which correlates with which is closest to the vector of king plus vector of woman minus vector of man, it's queen. You can also print the top 10 vectors here, and you will see that several of them are kind of like, I mean, it's not fully queen, monarch, princess is there. Then bunch of them are like prince, crown prince, etc. Probably because you're removing the man from the king, and probably it's looking at a younger version of the king or something like that. I don't know, but there are a bunch of queens there, and that the one with maximum correlation is queen. So this is very beautiful, right? So now let's look at another one. So now here we are calculating the similarity between different vectors. So okay, first of all, what does this mean? What this means is this vector embedding, it has meaning, right? So the vector embedding of queen is not something that is random. It is related to the vector embedding of king. It is related to vector embedding of woman and man in a mathematical way. That is why when we add woman to king and when we subtract the vector embedding of man from it, we get something which is very close to vector embedding of queen. So this vector embedding somehow is able to capture the meaning which one hot encoding cannot capture. Now if we print the similarity between woman and man, king and queen, uncle and aunt, boy, girl, nephew, niece, you will see that all of them have similar similarity score. But when you suddenly print something like paper and water, which are not related, the similarity score is much lesser. So indeed, all these words which are meaning wise related to each other, they have some kind of similarity score, but other two words which are not related to these in this way have a different similarity score. Let us look one last example here. So here what we are looking at is the magnitude of difference between man and woman, meaning you subtract the vector woman from vector man, right? So it's like a direction of gender. Direction meaning in that n-dimensional space, it's a direction that denotes the idea of gender. So you can see that if you do man minus woman or male minus female, they have kind of similarity scores, but when you do something like potato and triangle, it has a different score. Probably if I do boy and girl, I don't know, I have not run this, maybe the score will be slightly better. Let's see. Yeah, see, so now when I change this from potato triangle to boy girl, the score is now back to, it's in this range, it's in the range of 1.5. Whereas if I do something like phone and let's say duct tape. Oh, I guess I need a one word maybe. Yeah, see, so phone and tape, they have a similar different score of magnitude of difference between that is close to it's 3.7 plus. So this shows that indeed these vector embeddings have some meaning. Now let's come back to the presentation to go to the last part. I have to rush a little bit to also give Rajat enough time to go through his part. So the last part in this related to transformer architecture is retrieval augmented generation. So what this means is, imagine you have a pre-trained GPT basically, and training, as you know, is very expensive. Companies are spending hundreds of millions of dollars for training, so you don't want to train every single time. If you want to teach some new data to the transformer or to the this particular network, so how can you then incorporate new information and kind of get response which also takes this new information into account without spending money on retraining the whole thing? That technique is called retrieval augmented generation, RAG. Many companies really need this, like for example Amazon has a lot of customer inquiries on every single day. One of my friends working at Amazon says they have something like 100 million queries in all formats. So it's a huge expense for them because they need manpower for tending to that many queries. So they are trying to build their own chat bots for attending to those queries, and ultimately those chatbots, they have to be not just it should not be a general chat GPT. It has to be trained on their own, or it has to be at least should have some knowledge of their own database or whatever information they have. So RAG is a very important component of many of these companies, and I'm pretty sure all of you will benefit from knowing how to do RAG. I'll show one brief version of this. So there are two components. One is the language model itself, like for example ChatGPT. The second is the retrieval component. So retrieval component is whatever is the information that you are providing. So in my example, the example that I will show is, there is an amazing YouTube video about this. We'll be sharing the link. But the example that I will be showing is, this is a PDF document. I printed a website. So I went to a particular website today afternoon, and I asked, so this was regarding IPL. So there are a bunch of match statistics and the recent match between CSK versus GT, which was won by, I think, CSK, right? Yeah, CSK won, I think. So now let's see how we can train OpenAI's GPT on this particular PDF data and ask questions and get some responses. So we'll be sharing, so this is the notebook for that. Of course, we'll be sharing this with you. So here first what we do is, so you need to have an OpenAI API key. So we have hidden that because we cannot expose the key to people. But basically what we do is we use LlamaIndex here, which Rajat will be covering in some detail. But let me go to the final part, which is the fun part. I don't want to spend time here. So what I have done here is I have uploaded this IPL.pdf, which I just showed you here in this data folder. And what I'm doing is I'm reading this and converting it into a format where all the characters, everything is added into this. So if there are links, if there are other characters, so you can see that there are slash and new line characters. So every single text in this document is right now here. Okay, so this is now the representation of the new data which we want to use in the document. And then we create a vector representation of this data set, because we need the data in the form of embeddings. We can't use it in the form of English. So we do that. Sorry for skipping these parts. We are really short of time today, but I just want to show you the gist of what we are doing here. Okay, so once we have a query engine, which is something that allows us to ask questions from within this data, we can basically formulate any kind of question. So here I have written how many matches did RCB win so far, which are those matches. So I can create a query like this, which is exactly how you will be typing in ChatGPT, right? So this is an advanced version of that, where you can even tweak a bunch of parameters. You can teach the OpenAI GPT with your own data set. And the good thing is, yeah, so here when you run, the final response is RCB has won 5 matches so far. These are the matches that RCB has won. I don't know if this is correct or not. Maybe RCB has won 6 matches. But in any case, this may make mistakes, but here you can see the different responses it has generated. Like, so here we are asking to generate top 4 responses and a similarity cutoff score of 0.5. And here you can see that the cutoff score, similarity score of all of these are above 0.5. So it creates the top 4, it takes the top 4 responses, and all those responses will have similarity cutoff score above 0.5. So this is a very easy thing to do. We'll share the code with you, but I'll stop here and I'll give it to Rajat to make sure that we have some time to cover what we want to cover. But RAG is something that is easy for you to learn, easy for you to implement, and it's also highly valuable for many companies. So just try it out in its simplest form, and then you can go to more complex items. So Rajat, you can take over from here.
Sure. So in the last section, we'll be discussing about LlamaIndex and LangChain. So the reason why LlamaIndex is very important is because there are a lot of companies who would like to build applications which are specific to the documents that they are using. And currently, there are a lot of LLMs out there like ChatGPT, then Cloud, etc., who are trained on a huge corpus of data. And the problem is that this particular data is taken from all over the internet using several different documents. So they don't allow you to build context-specific applications, which is what LlamaIndex allows you to do. So LlamaIndex is basically something which provides you with a toolkit to bring or to develop context-specific LLM applications. So what do I mean by context specific? Let's say you get a job in a company related to Gen AI and who is working. Let's say that company is working on some specific problem and they are having some financial documents. Now they want to develop an LLM which can analyze their financial documents and can derive insights from it. Now this is a task which is very local and it's specific to the documents of that particular company. There is no use in using models which have been trained already on a huge corpus of data. So how do I go about doing that? Sridhar already talked about RAG, and if you looked at some part of the code in detail, it had LlamaIndex. So LlamaIndex provides you with very easy ways to query a document and to retrieve answers from it. So let's take a look at a simple example. So here we are looking at two documents which are Form 10Ks, which describe the revenues of companies, and here we are looking at Uber and Lyft. Now let's say I want to compare the revenue growth for both of these companies separately, and I want to derive insights from these documents. So this is the code which is written. It's a very simple code, and the reason it's so simple is because LlamaIndex has made it very simple for us. Now let's look at the different pieces of the code. Initially, you start off by importing libraries. These are standard libraries which you import from LlamaIndex. Then you configure the LLM service. Here they are using OpenAI. Then you download the data, which are basically these two PDF files, which I just showed you, and then you load the data. Then you use this function called vector store index. Now, in just one line, you can build indices, and this is one of the main contributions of LlamaIndex. It allows you to generate vector embeddings from the document. So vector embeddings would be something similar to which Sridhar showed. And then the final thing is something which is really interesting. It's called as a query engine. So what generally happens is that, let's say I query a document. In this case, the query is compare and contrast the customer segments and geographies that grew the fastest. Now, typically within a query, there would be subqueries. So, for example, what is the subquery over here? You can divide this query into analyze the growth for Uber first, then analyze the growth for Lyft, then analyze the geography for both the companies separately. So we are asking, so whenever we query a document, sometimes users ask multiple questions within the same query itself. So this query engine toolkit, it divides that one query into different subqueries. For example, here you can clearly see the division. Yeah, so so this particular query, which is one single query, it has been divided into 4 subqueries. The first query is what customer segments grew the fastest for Uber separately. Second is what geographies grew the fastest for Uber. And the third and the fourth are the same for Lyft. So one query is divided into 4 different subqueries. The answers for these 4 sub-questions are collected separately, and finally they are merged together. So when I print response, all the queries are merged together into one single reply, which is like this. And it's so easy to do that. So these toolkits have made LlamaIndex very popular and have made querying large sets of documents extremely popular. So this is in essence the meaning of LlamaIndex. It essentially has 3-4 different features. The first are data connectors, which allows you to connect the application. So let's say you can connect a PDF, as we just saw. You can even connect APIs or SQL databases. Then you can create very easy indices, like we just saw using the vector index function. You can index documents very easily. And then finally, you can use query engines, where if you have complex queries which the users have typed, you can break down these complex queries into subqueries, which can be used to query the document separately. And then finally, all these results are pulled together to generate one final response. Now you might be wondering, how do I create such an application? Now, if you look at applications like ChatGPT, ChatGPT is not an LLM. The LLM underneath is GPT 3.5 or GPT 4. ChatGPT is an application which is built on top of an LLM. So if let's say as a user or as a generative AI enthusiast, I want to build an standalone application. How do I do that? Okay, so I can build a model, that is fine. How do I take it from a model to the application? And that is what LangChain helps you with. LangChain actually provides you with a centralized environment to build LLM applications. So and one of the main USPs of LangChain is that LangChain has completely abstracted the coding process. So this is ideal for beginners. They have made building and deploying applications extremely easy. So so LangChain abstracts code and basically provides building blocks for generative AI applications. Now, why is it called a LangChain? It's because chains are at the core of any LangChain workflow. And what do I mean by chain? Let's say we want to piece together a prompt with an LLM in an application. So we can basically connect these features in the format of a chain, where first part of the chain is the prompt and the second part is the LLM. So you can use the function LLM chain, and in the bracket you can connect the parts of the chain, which is the LLM itself and the prompt which you are giving to that LLM. So by usages of these chains, you can actually build applications very, very easily. So they do have a website which looks like this, and there is a GitHub repo also. We'll be sharing the link of this repo also in the document that we'll be providing to all of you. So this brings us to the end of today's lecture. At the end, we also wanted to briefly touch upon the scientific machine learning bootcamp that we have started. So this bootcamp is, I'll just talk about this for 1 or 2 minutes, and after that we can answer some questions if anyone has any questions. So we have started this bootcamp for beginners who are interested to transition to machine learning. And this bootcamp, we'll also share the link in the chat. This has been prepared in mind, keeping in mind that people who, let's say, are working in a core area, whether it is engineering or any other field, and from that core area, they want to transition into ML by leveraging their expertise in the core area. then how do you do that? So scientific machine learning is basically a field which allows you to merge both the skill sets. One is the skill set in your core field, and the second is the skill set in ML, which can be very basic to begin with. So within this bootcamp, we have two versions. There is a beginner version in which we have created a passive course. Then we have a plan which is an active plan where we'll be assisting you to publish a research paper. We have already created the problem statements, etc. So it is a 3 to 4 month program where we'll be working with you to publish a research paper in this field. And it is really ideally suited for students who are serious in their journey and they really want to transition to ML. So if anyone is interested in this bootcamp, you can go through the link which we have mentioned in the chat, and the list of resources have also been shared in the chat for all of you. So just click on that link right now and just download all the resources for reference later. So I know that the number of resources that we have covered in today's webinar were quite large, and there can be moments in this webinar where you have probably found it difficult to follow, which is fine. But if you follow this path which we have laid down in this webinar very diligently, this can be a great start to your career in the field of generative AI, which can also help you to get jobs in the field. So this is really an excellent field, and you have made the right decision to start at this time where there is a lot of traction in companies as well. So with this, we will end the webinar, and maybe we can take 1 or 2 questions from the chat.
Yes, so thank you to first of all everyone to staying this late. We are like 7 to 10 minutes over time, but you stayed for this very long webinar, so thank you so much for that. If there are any questions, please put it in the chat. So people who have paid for the recording of this webinar will be getting it automatically after the end of the session through PubMed. So you'll receive it in your email. I have received some personal messages regarding the SciML bootcamp. So there are different plans of the bootcamp. There is a student plan, community plan, and a researcher plan, each of which offers separate benefits. So you can go to the website and search more about these plans to understand the differences between these three. Also, we hope this webinar is like a gateway for you to master generative AI and you are not too afraid of the subject anymore. We have tried to cover all the basics in generative AI in this webinar so that you can start your journey.
Yeah, we'll also be conducting more webinars which are focused on each of the components which we covered today, so that it's a bit more slow and we can spend more time on each of the components. But today we wanted to give an overview of what all things you can expect to learn. And don't worry if you did not understand some specific portions in today's webinar. It's completely natural, and we did not, it was not our intention to make you understand 100% of what we covered today. But if you got an overview and some idea of how things can be done yourself, or some confidence that things can be done by yourself, that is a great outcome from today's webinar. In the future webinars, we'll be covering things in much more detail. So we invite all of you to join for that also. And we'll be posting the details about that on our LinkedIn. So please connect with us on LinkedIn. Yeah, so, and if you have any questions about scientific machine learning bootcamp or LLMs or generative AI or anything that we presented specifically today in the webinar, you can email us.
So Saurav has asked one question we can take maybe as the last question in the oil and gas sector. So in the oil and gas core sector, right, there are a number of places where ordinary differential equations come into the picture. For gas flow, for oil and gas multi-phase flow, it's an amazing topic to apply or to think about scientific machine learning projects in the first place. So it's a great topic to apply SciML. In fact, I personally know some research topics which we can give to you if you want to publish a paper in this field. And Rehan has asked if traditional ML will also be covered. Yes, so we have a section meant for traditional ML as well. So you learn both traditional ML as well as integrating with your main field.
Okay. Yeah, looks like a good time to stop. Any other questions, guys? Feel free to send us an email since in the interest of time, and we'll be posting more details about the upcoming workshops, everything on LinkedIn. So let's stay connected. Thank you so much, everyone. Hope you learned something today. Looking forward to meeting you again all of in the next events.
Thank you so much, everyone.
Thank you so much, everyone. Bye bye.
Bye bye.
Thanks.
Bye.
Bye.